All right, 3.5, infinite limits. So let's say we have a graph. Let's say it's 2 over x minus 1, and it's the limit as x approaches 1. Okay, so at 1, as we're going to be talking about over and over again, something that you've learned in the past, and that's vertical asymptotes. And hopefully you remember that we have a vertical asymptote at 1. Now, determining infinite limits from the graph, if we would graph this and you would plot points and say we get closer and closer to 1, whether that's at 2 you'd get 1, if you put in 1.5 you'll get 4. Excuse me, you would get, if I put 2 in, you'd actually get 2. 1, 2. And then if I put 1.5, you would get 4. And then it will just keep getting increasingly big from there, right? It'll just keep shooting up and never touch, but we can't put 1 in. But as we get closer to 1, you get obnoxiously big numbers. And then on the other side of it here, as we get closer to 1 on the other side, whether it's 0, you would get negative 2. And at 0.5, you would get negative 4. So the graph would look something like that, okay? So how can we determine it's an infinite limit from the graph? Well, as we get closer and closer to 1, it's going to pause infinity. As we get closer and closer to 1 from the left, it's getting negative infinity. So therefore, we can conclude that the limit is equal to infinity. Now, in the past sections, we've said it doesn't exist. Either answer works. In this section, we're going to just keep calling these infinite. All right, here's a little bit of a formal definition of vertical asymptotes with relation to limits. If f of x approaches infinity or negative infinity as x approaches c, from the left or the right, then the line x equal to c is a VA of the graph of f. Okay, so it's pretty much saying what we were doing in the last problem. We're approaching from the left side on the last problem. We're going to negative infinity. If we went from the right, it was positive infinity. So therefore, it is a vertical asymptote. Using rational function, as we have talked about in the past, if we have c as the value and it makes the denominator 0 but does not make the numerator 0, therefore there is a vertical asymptote at x equal to c. So c is your VA. All right, 2 quick examples. Sometimes we have to factor. In this case on the left, we do have to factor. The numerator can't be factored. It's a sum of squares. Can't factor it. But on the denominator, though, that's an ugly 2. Let's fix that up. There we go. And values that make the denominator 0 are 2 and negative 2. So your vertical asymptotes are 2 and negative 2. 2 and negative 2 do not make the numerator 0. Please don't make the mistake. The other one, set x plus 5 equals 0, and you will get x equals negative 5 is your VA. Okay, so quick and easy. We found values that make the denominator 0 but not the numerator. Those are your vertical asymptotes. All right, let's find the vertical asymptotes of this. F of x is equal to x squared minus x minus 6 divided by x squared minus 9. So, of course, we need a factor, as we said before. So we're going to x minus 3 times x plus 2 over x minus 3 times x plus 3. X minus 3's cancel. Let's cancel them out to help us with the graph. And there's our new function that we're going to work with to find out our vertical asymptote. You have a vertical asymptote at x equal to negative 3. Now, 3 is not a vertical asymptote because that makes the numerator 0 as well. You're going to have a hole, okay? But in this case, at x equal to negative 3, we have VA. All right, so here are the properties of infinite limits. I will give you a moment to copy it down. I would suggest hitting pause and writing these down. All right, so let C and L be real numbers, and let f and g be functions such that limit as x approaches c of f of x equals infinity, and the limit as x approaches c of g of x equals L. This is whenever we have two different types of functions going on, we can separate them in some way sometimes to help us solve. First one is sum and difference. If you're adding the two functions together, it will go to infinity as your answer, assuming that f of x is going to infinity. The second part is the product rule. If you're multiplying f and g together, and the limit is approaching c for both, just like it says up top here, limit is x for c need to be the same thing. If your limit here, L, is greater than 0, it will be infinity. If L is less than 0, it will be negative infinity. Why? Because if L is negative, you'll be multiplying infinity times a negative number, which will just be negative, right? So that's why there's two parts. If L is less than 0 and L is greater than 0. 3. If g of x over f of x, we're finding limit as x approaches c of, it will be 0. Why? Because your denominator will be going to infinity. If your denominator is going to infinity, it's going to be 0. Okay? Similar to your horizontal asymptotes that we talked about in previous sections. If the denominator is going to infinity, it's getting bigger and bigger and bigger, it'll go to 0, making your fraction smaller and smaller and approaching 0. We'll do one example and then we'll call it a day of using one of our properties. So we have a limit as x approaches 1 of 1 plus 1 over x minus 1. What will your answer be? Your answer would be infinity. Why? Because of our first property of addition, right? This goes to infinity, so therefore the whole limit goes to infinity. Okay? Thank you for watching, and we'll see you in class. Bye-bye now.